Good morning. I'm Bhavani Thuraisingham from the University of Texas at Dallas. I would like to thank the organizers for inviting me to give this keynote address at ParSocial 2020. I believe this is the first virtual ParSocial workshop, and I'm really honored to give this presentation. My talk will be on the role of artificial intelligence and cybersecurity for social media. So the outline, I've got a number of topics, all related to cybersecurity, AI, and social media. In part one, I'll focus on integrating cybersecurity and AI, and in particular, I'll talk about big data security and privacy, because at the heart of cybersecurity or AI is data, and massive amounts of data are being collected. So I'm going to talk about the topics that I've marked in red. So then I will discuss ensuring the privacy of individuals, because the more data you have, you've got to make sure that the individual's privacy is maintained. Part two, I'll discuss machine learning for cybersecurity, and in particular, the focus will be on insider threat detection. Part three will be on cybersecurity for machine learning, because what happens if the machine learning techniques are being attacked? So that area is called adversarial machine learning. Then in part four, I will discuss social media, cybersecurity, and AI, in particular, AI and data science for social media, because the number of AI applications, right? And the application I'll be focusing on is location mining. And I will discuss the security and privacy aspects for social media, and then talk about a particular social media system we developed in the cloud. Part five will focus on an analogy between social media and security and AI and Internet of Transportation. Then part six, the role of AI and cybersecurity in social media, in particular the applications, and then summary and directions. I would like to thank our sponsors, National Science Foundation, Army Research Office, and Air Force Office of Scientific Research for sponsoring our work over several years, and my colleagues, Professors Murat, Kantarcioglu, and Latifa Khan, for working with me, and our project coordinator, Ms. Rhonda Walls. So part one, integrating cybersecurity and AI/data science. As I said, massive amounts of data are being collected, and this is partly due to the technological advances. So it's now possible to capture the data, process, analyze large amounts of data for a variety of applications, including for cybersecurity tasks. Because for instance, if you want to analyze the attacks, you've got to collect lots of data about the attacks. So the cybersecurity tasks include, say, user authentication, access control, anomaly detection, user monitoring, insider threat protection, so a number of applications. By analyzing all of the data collected on the web, as well as other sources, we can identify the connections and relationships, and this could help us with a number of applications such as homeland protection, disease outbreaks. In fact, we are facing it today, right? With COVID-19, AI and data science and the massive amounts of data being collected is helping us to pinpoint the hotspots. And of course, homeland protection, we know that, after 9/11, the terrorist attacks, data was collected to analyze what are the potential hazards. So we collect data, even if it's anonymized, we can remove identifiers and so on, but we can link various pieces of data together and the privacy is violated. So the security tasks such as authentication and access control could require detailed information about users. And we cannot afford that information about the users to be stolen or misused, because it can lead to privacy breaches. So some of the directions that we have explored are access control models, privacy enhanced techniques, big data analytics. We also call it data science, machine learning for cybersecurity. Okay, so here is a little sort of example how we can use data mining, data science, and security and privacy together. So back in 1996 at the IEEE 11.3 conference, so it was ages ago, 24 years ago, I gave a keynote address on data mining, security, and privacy. And a version of that address was also given at the Pacific Asia Knowledge Discovery Conference in 1998. And then I was at NSF in 2002, and I wrote a seminal paper on data mining, security, privacy, and civil liberties that spawned a whole new area of research. And that was called privacy preserving data mining. And today we have privacy preserving data science, privacy preserving machine learning. So the whole idea is to take the original data and perturb it and or randomize it. So add a bit of noise and then work with the modified data, and the end result should be the same, right? Meaning that there shouldn't be much of a difference. If we were to figure out that people with certain conditions, right, or certain parts of the country are more susceptible to, say, diabetes or maybe even COVID-19, then those results, we should be getting it even after we have perturbed or randomized the data. So later on with our student, Dr. Li Liu, we focused on privacy preserving decision trees and using the perturbation method. So with big data, security and privacy, data mining or data science has been exacerbated because the more data we have, the more people we have to protect. So we had a workshop in September 2014 at UT Dallas. It was an NSF workshop to look at various aspects of big data security and privacy. And then we presented our results at an interagency working group in Washington, DC in February 2015. And I believe some research efforts were spawned by government agencies after that privacy workshop in 2015. Okay, one area of research that we have been carrying out is privacy aware quantified self. So we've got your smartphone, and in there you can collect all kinds of health related information, right? Your fitness data, location data, social media data, image, videos, and other data sources. And some of the data could be encrypted and backed up in a cloud. Some you can anonymize and share it with others, and also share the query results. But regardless, our contribution was policy-based data collection, data storage, data analysis, data sharing. So policies should guide what data we collect, what data we store, and where do we store it, and how do we analyze, and how do we share the data. So what we did was the following. So here's our framework, right? Cloud sharing and local data store and the mobile apps. So as more data is collected, right, you cannot store everything in the device. So you have to use some kind of a cloud storage. And based on the policies, local apps running on the device will be given access to various pieces of data. And in some cases, you don't have to store all of the data, because for a 20-year-old person, do you really need to, count all the weigh that person every minute or every day? No. Maybe you can weigh that person once a month. But for certain other people with some conditions, you may have to weigh them every day and store the data, right? And in some cases, you've got to delete the data, right? So what are the policies governing data deletes? And then we envision that data sharing and results will be carried out as services running in the cloud. So how do you anonymize the data? So based on different scenarios, some of the data could be sent without any modifications, such as heart rate for medical diagnosis, and some will be sent after sanitization. Okay, so that sort of gives you some idea of the first part, big data security and privacy. Our part 2 is machine learning for cybersecurity. So what do we do here? Our focus has been on stream classification, big data stream mining or big data stream analytics. You can call it stream machine learning or stream data science. So we use the past data to build a classification model. You can predict the labels of future instances using the model. We can help with the decision making. So what is big data streams? It's continuous flow of data. Very common in our connected digital world, and massive amounts of data being collected. So it's coming in data streams, and then we build a classification model. Now, the challenge here is to build models that are evolving, right? So we build multiple models, and then we throw away the models that are of no use. So if the data is too old, we can throw away the models built from that data. So as new data comes in, your model has to evolve, right? So you train, right, attack traffic, you block and quarantine, and then benign traffic, of course, you go to the server and store the data. Of course, periodically, the models have to be updated. And that's a challenge. When do you update the models, right? But yes, because you have to update the models. So it's sort of like what we are hearing today, right? Test, trace, and isolate, right? So you test, and then you trace, and you isolate. So you later on, then you train the models, and then you test. Okay, so we applied it for insider threat detection. So what's insider threat detection? So there are people and processes who may behave, who may seem like normal people, right? Non-malicious people, but they could be really corrupt and malicious. They can masquerade and stay inside the machine or inside an organization and do all kinds of bad stuff, bad behavior, and cause anomalies and cause many attacks. So we have designed and developed an ensemble-based stream mining, you can call it stream analytics, stream data science technique, based on, first we did supervised learning, and it addresses the challenge by maintaining an evolving collection of multiple models. Our models are changing, they are evolving to classify dynamic data streams of unbounded length. And data streams are continuously arriving. So the classifier we developed, right, and it has got very good accuracy based on our results that we obtained, traditional support vector machine and one-class support vector machine and other single model approaches. We have also designed and developed unsupervised ensemble-based learning algorithms. And these algorithms maintain a compressed dictionary of repetitive sequences found through dynamic data streams of unbounded length to identify anomalies. Again, the challenge is evolving models, unbounded length. In unsupervised learning, compression-based techniques are used to model common behavior sequences. So the results of in a classifier exhibiting a substantial increase in classification accuracy of data streams containing insider threat anomalies. So our ensemble of classifiers allows the unsupervised approach to outperform traditional static learning-based approaches. Okay, so our results have been published in a number of conference and journal papers. So here is, I give one reference here. So what happens, data is broken up into chunks. So here what we do is K chunks arrive, right? So we gather data from chunk K. So let's say K minus 1 chunks have already, or Ki minus 1 chunks have already arrived. So we have developed models. The Ki chunk arrives, and then we update the models, feature extraction and selection model updates. Then we learn unsupervised graph-based anomaly detection and supervised one-class SVM. And then the K plus 1 chunk arrives, we extract features, and then we do testing. For testing, again, we use this ensemble of models. We've already trained the system, and so we test it, and it will tell us if it's an anomaly or not. Okay, this is typical in most data analytics, machine learning, data science algorithms, but again, the challenge for us is to develop this ensemble of models for evolving data of unbounded length. So that finishes machine learning for cybersecurity, but there's another part, cybersecurity for machine learning. And this is an area that has received lots of prominence, especially with the cybersecurity community. because this whole area has come to be known as adversarial machine learning. Because what happens if your machine learning techniques are attacked? So for instance, with my colleague Dr. Murat, we have developed a number of adversarial machine learning algorithms. What is it? It's not concept drift. It's not about online learning. The adversary is adapting to avoid being detected. So during training time, it could happen, data poisoning, during testing time. Eventually, it becomes a game between data miner or a data science technique and the adversary. So we have these red boxes, which are the bad cases. That means these are the positive instances, meaning that they are indeed attacks. The blue are actually benign cases. So this is the boundary, right? The support vector machine boundary. What the adversary is trying to do is learn our algorithms, learn our data, so that it knows exactly how we are going to do the classification. And so it's going to push these red things into blue, red squares into blue circles, right? It's going to try and push it so that the bad instances are going to show up as good instances. But in time, we will know the adversary's game, so we are going to change our model. So we are sort of, playing a game with the adversary. Then after a certain time, adversary knows that we have adapted our model, and the adversary is going to figure out what our model is, what the data we are using, and it's going to thwart our model. So it becomes game playing, and eventually we want to beat the adversary. Okay, so our work is discussed in a paper, and in the next chart we'll show the paper. So we considered a number of attacks, targeted attacks, or the free-range attacks. Free-range attack, the adversary can move malicious data anywhere in the domain between the lower end, lower bound, and the upper bound. So between these 2 points, so for every j is in 1D, an interval, CF is between 0 and 1, and xj is the largest or smallest value of the jth feature of a data point, xi, that xij can take. Okay, so the details are in our paper. So it's a free range attack, but in reality, you can have the free range attack or several targeted attacks. So here's our the gist of our work, and published in KDD a few years ago, 2012, I believe, our first paper on adversarial machine learning. That's the Knowledge Discovery in Data conference, a top data science conference. So what we are trying to do, right? So this is the boundary support vector machine. We are pushing it to the blue line. Okay, black dashed line is the standard SVM. But remember, we are trying to figure out what the adversary is up to. So the positives, which means it's a bad thing, bad attacks. The others crosses, and the green circles are the benign ones, right? So what the adversary is trying to do is to push a lot of the bad stuff as good stuff. So what we have done here is moved our boundary line to this blue line here, so that we can catch some of the stuff that really is pretending to be good, but it's bad. So a threat model, test time, deployment time attacks. Attacker modifies X to X prime. We could modify the packet length by adding dummy bytes, or add a good word to spam email, add noise to an image. And so the whole idea is for us to create this blue line. But we can really push it so far that we can catch almost all the bad stuff. But then if you move it to a point, even the good stuff is going to turn out to be bad attacks, right? So the challenge for us to really figure out where this blue line is. And so this paper is quite interesting, actually. It gives all the details about how we get this blue line. Adversary is trying to learn what we are doing and modify its behavior. We are trying to do what the adversary is doing, and then we are trying to modify our models, right? So it becomes game playing between us and the adversary. Okay, so that finishes part 3. Part 4 sort of combines everything: data science, security and privacy, and social media. So as I said, social media systems can be analyzed to figure out a number of things. In the case of pandemic, we can try and figure out where is the hotspot, right? For that, we need to also maybe have to find the locations. If we want to do some marketing, we will want to find the location of the people, right? Very often they switch off the location in their cell phones or smartphones or whatever. But we want to find their location. No point marketing a pizza parlor in Los Angeles to someone living in Dallas, Texas. So the whole idea, and I'm putting it very simply, to find John Doe's friends. And that's called location mining or location analytics or location-based machine learning, whatever. So we look at all the friends, and it's sort of you are like your friends. But yes, the friends may have moved to Arizona, for instance. So we've got to take that into consideration. The simple way, we find that some friends, so friend 1 could be in Dallas, maybe in Seattle or Richardson or Sydney. Friend 3 is in either Austin or Minneapolis. So, but you can find that some people would say Dallas, but it could be Richardson, Texas, which is bordering Dallas, which could be Plano, Texas, also bordering Dallas. So we can combine all of that, and we come to an algorithm. We developed an algorithm called agglomerative clustering. So we take Dallas, Texas, Richardson, Texas, and Plano, Texas, and combine it together. It sounds very simple, but when you actually go to do it and combine various pieces, it could get quite complicated. So the gist of our approach, our contributions, we developed 3 graph-based location mining algorithms for online social networks. It maps the location mining to K nearest neighbor. It's a type of data science technique, semi-supervised, and graph partitioning problem. So it outperforms some of the other approaches like content-based approaches, relationship between geospatial proximity and friendship. That's one idea behind it. And we also look at the effect of geographical mobility on current location of users. Okay, so this is our work on location mining. The other part is privacy. So we know that data science, machine learning, data mining, whatever, is really, it's very important to extract those nuggets and the special properties for social media systems. Who is the gang leader? Who is the leader of the group, right? To answer those questions, where is he staying? Is he in Dallas, Texas, or Los Angeles, California? Who are his friends or her friends, right? But then in certain cases, we've got to protect the privacy, or in many cases, we need to protect the privacy. So we did an experiment to figure out who is liberal and who is conservative, right? My colleague Murat Kantarcioglu actually did this work. And we got a lot of coverage for this because at the same time, around the same time, MIT had done some work on detecting or predicting who is liberal and, who is gay and who is straight, right? So of course, if MIT does something, that attracts a lot of coverage. And so we were also grouped into that article. So we got coverage from ABC News and Boston Globe and so on. So we looked at 167,000 profiles from Facebook, restricted to public profiles in DFW. So we had over 3 million links. So you can see the diameter is 16, the largest component. Number of nodes or profiles, 167,000 something. Number of friendship links, 3 million something. Total listed traits, 4 million something. Unique traits, 110,000. Number of components. Components are disjoint pieces, 18. The probability that's liberal is 45% and probability conservative is 0.55. So you can see, okay, all the obvious traits, right, we removed in our analysis, because if someone tells you he or she says that you must legalize same-sex marriage, it's really hard for that person to be a conservative. So these are some of the liberal traits: legalizing same-sex marriage, Every time I find out a cute boy is conservative, a little part of me dies. These were actual traits. Equal rights for gays, the Democratic Party, government religion is a disaster. These were some of the liberal traits. And we also had some conservative traits, which we removed and then did an analysis. And we have a paper that we published. I believe it was in World Wide Web Conference. And it had, we had some pretty accurate results. And in fact, my colleague really followed up. It was an experiment that he did with a particular television channel. And he followed a couple, and with all the stuff that they were posting on Facebook, he was able to, he and his team were able to find out so much information about the couple. And later they interviewed the couple and my colleague. It was really a very interesting exercise that they carried out. Okay, so that's a privacy. But then what about security, access control? You can't simply have access to everything. And currently Facebook doesn't offer fine-grained access control, right? It offers access control, but it's more coarse-grained. So we use semantic web rules language, SWIRL. The social media network we used in this particular case was POF, friend of a friend, that has been developed among the semantic web community. So example of a SWIRL rule, the target object, the video, is controlled by the parent of Bob, means parent of Bob can control whatever Bob sees, right? So here, if Bob is the owner of an object, say a photograph, then all of Bob's friends can see that object, see his photograph, right? So here, if the target object is, here Bob is the owner of the target object. Here Alice is the target object. So it's Alice's photograph. All of Alice's friends can see her photograph. And rule number 4 is sort of a generalization of the previous rules. So with this, so what is the research challenge? Research challenge for us is to carry out query rewriting and also rewriting the SWIRL rules in such a way we can have efficient execution. And then we developed a system, secure social media framework architecture. And in fact, the paper, we published this paper in ACM SACMAT. It's a top tier access control conference. And this was published in 2009. And 2019, last year, 10 years later, we got the 10-year Test of Time award. So we were quite pleased about it. So we have the reference monitor. That's what it controls all the access. It must be secure and trusted. We have the social network application, the semantic web reasoning engine. We have all of the policies in SWIRL and the knowledge base. And so the reference monitor will control all access. And we essentially implemented these policies to see who can see what information, right? So if Alice's friend is querying something, if she wants to find information about Alice's videos or photographs or whatever, you look at the rules and she is indeed a friend of Alice from FOF, you can get that information and then you can grant him or her access. Okay, so what we also did was to implement secure social network in the cloud. Why a cloud? Because regardless of what, whether we are doing AI, data science, cybersecurity, social media with massive amounts of data, you have to be able to scale, right? You cannot wait forever for a request to be processed. So we need high performance computing, and that's why, and I'll point this out later towards the end of my talk, scalability is crucial, right? We need scalable solutions, and that's why ParSocial is in a very good position, the members of ParSocial, because they're working in social media, data science, whatever. They are also looking at parallel processing and high performance computing. You have to bring it together. So what we did was to develop all of these technologies, right? We used Hadoop MapReduce, that's sort of what we call the cloud. Then all of our data was in RDF, Semantic Web Resource Description Framework. We built policy engines and a query engine. And then we had different social media and people communicating. And we we had designed the system, we didn't complete the complete implementation. We did part of the implementation about different organizations sharing data. And the whole idea is to apply this to a number of applications. For us, it was about emergency preparedness application. So again, these are policies, right? Agency 1 can tell agency 2, I can share you some data, some emergency preparedness data, provided you don't share the information with another agency, right? With agency 3. Now, these days, this is becoming so important, especially when we are trying to find a vaccine for COVID-19, and many countries, US, Europe, UK, France, Germany, China, Singapore, Australia, they're all working, Japan, they're all working towards a vaccine. And some countries may want to find out what the others are doing, right? So they may hack into other people's computers to get the information, whatever. And so the whole idea is, because remember, whoever wins this, right, is going to have huge payoff in terms of financial and also societal benefits, right? Because we absolutely need the vaccine. So different groups, so instead of social networks, we can call this, a research group in particular agency, another research group, but they all form sort of a close collaboration. And we call it social network. Okay, so we implemented parts of it, not the complete application, but this is something that's going to be really important, especially for what we are striving to do today. Okay, so the next topic is an analogy, Internet of Transportation. So one of my PhD students in cyber-physical system, he just finished his defense. And so what he's been working on is the whole thing of Internet of Transportation. What do we mean by that? Just like Internet of Things, your home computer is connected to what? Your refrigerator, to your television, and to your various other gadgets that you may have at home. They're all interconnected. Similarly, on the road, all of the cars are connected to each other. They are connected to the trains and to the trucks and to the fire office, fire station, to the police station. Everybody is connected, right? It is already there, but not quite. It's going to be the future. And the cars could also be driverless cars. And so what is the challenge? What is the analogy? Just like we have connected people, we have connected things, right? And the human may drive it. So all of the folks who are driving the cars will form a particular network. It could be, we call it social network, but this is really like a transportation network. And so there are many similarities. So what my student did was he came up with a physics-based anomaly detector. So he built something, a reference monitor. Remember, in security terminology, reference monitor is that part of the system that controls all security access. So he built a reference monitor using a physics-based anomaly detection. That algorithm is called PPAD, for ground and aerial autonomous vehicles. So you have ground vehicles and aerial vehicles. So the algorithm consists of 3 parts: offline pre-processing, building a model offline of the AV's physical invariants, right? Then that's using the various physics equations. Then you implement an online tool to monitor expected and observed behaviors to detect the anomalies. And so if there is a significant residual difference exists between the executions, then you raise an alarm. So you have online verification and then anomaly detection, you raise the alarm. And the paper based on this work has been accepted at the Unix Security Conference. It's a top tier cybersecurity conference. Okay, so that's physics-based anomaly detection. What I'd like to also explore in the future is how do we bring data science AI into this transportation security? So Internet of Transportation is subject to attacks, just like any other cyber-physical system. These systems have to work together and they have to collaborate, right? Just like in social media, the people work together. It's not just a question of posting photos and so on. They can solve some problems together in the same way Internet of Transportation, connected vehicles having to work together. Streaming data, right? Sensor data, it's streaming. It's being collected from such systems, including autonomous. And in future, we are going to have driverless vehicles. As transportation systems go electric, we need more energy conservation. So threats to the security of such systems could cause massive damage. That could include accidents, loss of lives, as well as stranded on lonely highways due to attacks on the energy management systems. So we could use data science ML techniques, right, to analyze the data. So remember I talked about stream analytics for inside a threat. Can we use some of those techniques to analyze the data that's being collected in Internet of Transportation systems, right? So again, continuous data, streaming data. So can we apply those techniques? That means, can we come up with the evolving models, okay? An ensemble of models. When data is evolving, the models will also be evolving and then detect anomalies. So essentially, how can we integrate our anomaly detection data science-based systems with the physics-based systems and integrate the two? Of course, the adversary will be learning our models, okay, used by the vehicles, and learn about the data used in the training, and the adversary is going to attempt to thwart the vehicle's learning process. So vehicles models or algorithms catch on to what the adversary is up to and then adapt. So that's going to be, I believe, the future. Us playing games with the adversary and winning, beating the adversary. The main question is to understand the nature of the complex transportation data and adapt the stream analytics techniques and apply them on the massive amounts of heterogeneous sensor data being collected. Okay, so the part 6, this I believe is the last part. What's the role of AI and cybersecurity for social media? So I talk about 3 applications. One is fake news. So what's fake news? We have heard it quite a bit, right? After the elections, 2016 elections, we've all been involved in one way or another to come up with techniques to detect fake news. When I say all, most of us. Machine learning techniques are being applied to detect fake news in social media. How do you do that? We've got to train from numerous articles, right? We've got to train the model with fake articles and good articles, right? Honest articles. We also may want to use some data provenance analysis and to determine the source of the fake news, which is not easy, but combining that with examining the articles, the content of the articles, perhaps we could try and figure out maybe where did the attack come from, or where did the fake news, where was it generated from, and is the article fake or not, and how much of it is fake. It would be nice to be able to analyze it and look at, do some fine-grained analysis. Of course, security exacerbates the problem, security attacks, because the fake news could emanate not just from humans, right? I could post something really bad about someone, but that's something they could perhaps trace it to me. But what happens from some unknown address, IP address, can release a series of malicious bots. And these bots could be trained to create the fake news. So then the bots are being trained, right? You're using cyber attacks and AI to train the bots. They've got to know exactly what time, when and where should they release the fake news. So that could be even more dangerous than, say, a person releasing fake news. So, because with bots, you absolutely have no idea. There could be millions of bots from all over the place, okay, generating this fake news and making it look very real. So this is a major challenge faced by AI, data science researchers, as well as cybersecurity researchers and social media researchers. They all have to work together in order to be able to detect fake news, right? So this is a big problem. Another problem, of course, what we are going through today, COVID-19. Without a doubt, machine learning is helping, right, to detect the spread of the disease. So for instance, The White House, I believe, is looking at the University of Washington model, the Institute of Health, I think, metrics department. They have developed a great model that the White House is using. And the New York State, the Governor Cuomo had mentioned, actually this morning I was listening for a short while, and he's using the Imperial College London model. So there are a number of good models that are being used to make some predictions, right, and projections. So the problem is data privacy, right? So while we are able to say, figure out when and where these outbreaks are happening, who is being attacked, meaning who is getting the disease, attacked by the COVID-19 virus. So some people may not want to tell everyone, right? Because they want to protect their privacy. They don't want the whole world to know that they got COVID. So how can the data privacy be ensured? My colleague is looking at genomic privacy for the COVID data. And so how can genomic privacy be maintained? And then appropriate access control techniques, right? Who has access to which parts of the models being developed, which parts of the results? And then what about malicious attacks on the models, the training data and the results? Okay, we could be using the University of Washington's IHME model or the Imperial College's model, but what happens if the model and the data used to train the model is attacked? The model will be useless. And so we've got to be able to determine, right, that the attacker is onto us and we have to adapt. So that is going to be a major challenge. Over and over again, this problem is something that we are going to be faced. We've been looking at, we've been faced with, and we are going to be faced with more and more. Not just for COVID and fake news, even companies, right? We want to, the vaccines, right? We want to put out, be the first to publish the vaccine. Somebody could attack, right, and get our, comparative strategy or whatever, and they could supersede us. So there are a lot of consequences. The third area is AI for social good, right? Everyone says AI is for social good. Without a doubt, AI can be used for the good of the community, such as detecting the hotspots for COVID-19. But how can AI be good in the midst of cyber attacks and privacy violations? So artificial intelligence techniques being applied to solve security problems, yes. Detecting the spread of diseases, such as emergency preparedness, education, child trafficking, very, very concerning, violence against women. There's also developments in fair AI and bias in AI. You don't want the AI algorithms to be biased, and you want the algorithms to be fair. The technologies being developed for social good are also causing problems. Why? Because you can apply all these machine learning techniques and extract patterns and trends that could violate the privacy. So for small children, right? When I say children in general, you want to give them technologies so that we can monitor and figure out who is attacking them, who is abusing them. But we can, if we are bad, we can use that, right? Somebody could hack into the system, the attacker could figure out where these children are and go and attack these children or kidnap these children. Because by giving the technologies to the children, which they must have in order to protect them, but their privacy could be violated. That's the biggest worry I have. Even worse, the machine learning techniques themselves may be attacked, and that could cause massive problems. And that's where I say we need adversarial machine learning. Okay, so this brings us to the end of my talk, summary and directions. Okay, summary and directions for the role of AI and cybersecurity in social media. Without a doubt, numerous benefits of AI, including for social good, but we need to ensure cybersecurity and privacy. AI being applied to social media for detecting fake news, spread of COVID-19, number of other applications. Who are the leaders of the gang, etc. What about the security and privacy implications, right? So the privacy of the individuals who are getting sick could be violated. Privacy of the children could be violated. AI being applied to social media for detecting fake news, both the content and the source of the attacks. But what if the attacks are due to cybersecurity violations? How can we find out who the person is who unleashed all these bots? It's much harder. And we need solutions. That's something I really want to stress to this community, the ParSocial community. Scalable solutions, because you all are in a very good position because you understand parallel processing, high performance computing, and so on, and data science and cybersecurity. So all of that they have to work together. So the cloud, I mainly have looked at cloud for enhancing the speed. Parallel processing, in some cases, we have parallelized the algorithms, the data science algorithms, and high performance computing. So all of that they have to come together to bring together AI, cybersecurity, and social media so that we can develop scalable solutions. What's the point in having the best data science techniques when we may have to wait 10 minutes for an answer when we want that answer to be in 10 seconds, right? So scalability has to cut across our integration platform, integration of AI, cybersecurity, and social media. I showed one picture, remember earlier, where all of these agencies and various social media, they have to share information, such as for emergency preparedness or for detecting COVID-19, whatever. But whatever platform, we built that platform on the cloud, and our cloud at that time was Hadoop MapReduce framework. So we need to come up with scalable solutions if we want to integrate AI, cybersecurity, and social media, because remember, we are going to be, for these technologies, are going to be working on massive amounts of data that goes back to my, which is big data, security, and privacy. So you have massive amounts of data, you are applying AI and data science algorithms to extract the nuggets, which are going to be useful, including in social media, which is so critical, especially now with this COVID-19. We've seen how useful social media is. And of course, we've got to ensure that appropriate people, authorized people have access. And most important, we've got to protect the privacy of the individual. So scalability, big data, artificial intelligence, cybersecurity, social media, these are not just buzzwords. These are real words, because all of these technologies have to work together if we are going to combat a lot of the challenges in front of us. And the immediate challenge that we have, of course, is the COVID-19 pandemic. And once again, I would like to thank all of you for listening to this presentation, as well as to the chairs, organizers of the conference, for inviting me. And I will be happy to answer questions. Thank you very much.